So imagine opening every single door and window to your house, unlocking the safe, and, then just going on a 2-week vacation.
I mean, you would never do that in the physical world. It's just absurd.
Right, it's completely ridiculous. But right now, today, you might actually be doing exactly that in the digital world without even realizing it.
Oh, absolutely. People do it every single day.
Welcome to the deep dive. Our mission today is to unpack a really fascinating set of source notes from a CCNA module on network security fundamentals. It's originally from Suella Technical Community College.
Yeah, and the goal here is to sort of distill the mechanics of network security. We're looking under the hood of how these digital fortresses are built and, well, how they're broken into.
Exactly. And we're not just going to list off a bunch of technical jargon. I want to explore the psychology, the human error, and the sheer audacity of the attackers who are looking for those open windows.
It's such a critical shift in perspective, really.
Yeah.
When we talk about cybersecurity, I think the instinct is to focus purely on the machines, right?
Like the firewalls, the encryption, that kind of thing.
Right, the hardware. But the reality of modern network defense is that the technology usually the most robust part of the system.
Really? So the tech isn't the problem?
Usually, no. The weakest link, the vulnerability that attackers are actively scouting for, is almost always the human element.
Wow.
Yeah, that home security analogy holds up perfectly because essentially we are just translating human negligence into ones and zeros.
Okay, so let's get right into the minds of the people who are testing those digital windows. We are talking about threat actors.
Right.
These are the folks, or often like highly organized groups, who gain unauthorized access to a network. And once they're inside, the sources say they generally pose 4 specific types of threats.
Yeah, let's break those down.
So the first is information theft. I mean, this is basically the digital equivalent of breaking and entering to steal confidential data, right? Like stealing a company's R&D files or proprietary blueprints.
Exactly. And that leads directly into the second major threat, which is identity theft.
Which is obviously a lot more personal.
It is deeply personal. It's a specialized form of information theft. There's stealing personal identifiers, social security numbers, banking details, dates of birth.
So it's not corporate espionage, it's literally impersonation.
Right. The goal is to apply for credit, empty your bank accounts, that sort of thing. It's a multi-billion-dollar shadow economy driven entirely by harvesting human identities.
That is wild. Now, I want to pause on the next category because this is where the danger seems to multiply in a really insidious way. We have data loss and data manipulation.
Yeah, this is a big one.
So data loss is essentially destruction. Like a threat actor drops a virus that completely reformats a server's hard drive. All the records are just gone.
Which is a massive disaster, clearly.
Right, but isn't manipulation actually far more dangerous? I mean, if my hard drive is wiped, the alarm bells are ringing immediately. I know I've been attacked.
You know right away, yeah.
But if someone sneaks in and just quietly changes the numbers in a financial ledger, or, say, alters the price of a monitor from $299 to $199 on an e-commerce site, that rot could go unnoticed for months.
You hit the nail on the head. That touches on one of the most vital concepts in security, which is the difference between availability and integrity.
Okay, unpack that for me.
So, data loss destroys your availability. You need a file, and it is simply not there. The damage is acute, but like you said, it's obvious.
Right.
But data manipulation destroys integrity. If a threat actor alters records without authorization, they shatter the fundamental trustworthiness of the entire system.
Oh, wow, because you don't know what's real anymore.
Exactly. Imagine a hospital database where patient blood types are subtly altered. The data is still there, the system hasn't crashed, but the information is now weaponized.
That is terrifying. A breach like that could just linger silently.
Yeah, causing catastrophic downstream damage before anyone even realizes the system was compromised.
Yeah.
You literally can't trust your own screens.
Man. Okay, so the fourth major threat is disruption of service.
Think of this as the threat actor just crowding the doorway so legitimate customers can't get inside.
Like when you try to buy concert tickets and you just get that spinning wheel of death.
Yes, exactly. Or a 503 service unavailable error on your bank's website. The attacker is flooding the target server with so much garbage traffic that the server just collapses under the weight of it.
Locking out the real user. So human greed, malice, or just a desire to cause chaos drives these threat actors. But they don't use magic to get in, right?
No, not at all. They have to find an inherent weakness.
A vulnerability. Let's talk about how they find these open doors. The source material divides these into logical vulnerabilities and physical ones.
Right. Let's start with the logical side.
Okay, so we have technological vulnerabilities. This refers to weaknesses baked into the software or the protocols themselves, like TCP/IP.
Yeah, and to understand that, you have to think of TCP/IP as the fundamental postal system of the internet. It was designed decades ago with one singular goal:
Yeah.
get a message from point A to point B reliably. It was built by researchers who, honestly, largely trusted each other.
So they weren't building it with security in mind.
Not really. It was not originally designed with the assumption that the mail carrier might be malicious. So the protocol itself has inherent trust baked into its foundation.
And I'm guessing threat actors constantly look for ways to exploit that.
Oh, absolutely. Add an unpatched software or some outdated hardware, and you have a massive technological vulnerability.
Which brings us to configuration vulnerabilities. And this is where the user actively shoots themselves in the foot, right?
Pretty much, yeah.
Like, think about that brand new Wi-Fi router your internet provider mails you. If you plug it in and never change the administrator password from admin or password 123, you have a configuration vulnerability.
Exactly. You might have state-of-the-art encryption technology in that plastic box, but you just left the default key sitting right in the lock.
So it's basically useless.
Well, a security device is only as strong as its configuration.
Yeah.
Leaving default settings active, failing to enforce strong passwords, or even, leaving JavaScript universally enabled on untrusted sites, these are all configuration failures.
You have the tools, but you haven't bothered to turn them on.
Right.
But the third logical vulnerability is the one that really caught my attention in the notes. Policy vulnerabilities.
Oh, yeah. This one is fascinating.
We're talking about missing disaster recovery plans, sure, but specifically office politics. How do corporate turf wars literally create a network security hole?
It happens all the time.
It just implies that human ego is just as dangerous as a faulty firewall.
It absolutely is. I mean,
Yeah.
imagine a massive organization where the marketing department and the IT department are constantly at war.
A tale as old as time.
Right. Marketing wants to launch a new promotional web app, but IT has a, let's say, 3-month security review process.
So marketing just bypasses them.
Exactly. They use a corporate credit card to spin up a cloud server on their own, totally outside of the IT department's purview.
Oh, no.
And that server is unpatched, it's unmonitored, and it's sitting entirely outside the company's security umbrella.
And a threat actor scanning the internet doesn't care about internal office politics?
Not at all. They just see an unguarded server acting as a direct bridge into the company's data. Unenforced policies and departmental silos create these massive, invisible blind spots.
So human ego leaves the digital window open?
Every time.
But we can't forget the physical world. Physical vulnerabilities bypass all the digital locks entirely. If a threat actor can physically touch a server, they can break into it.
Yeah, physical access is game over.
The notes break this down into 4 classes. You've got hardware threats, like someone literally smashing a router. Environmental threats, like extreme heat. If the AC fails in a server room, the equipment cooks itself.
Yep, and electrical threats, like voltage spikes or brownouts that can fry the components.
But then there's maintenance threats.
This is a big one that people overlook.
A disorganized, poorly labeled mess of cables in a server closet. It's not just an eyesore, right? It's a security risk.
It's a critical security risk. If a network is under an active cyber attack, and the engineering team needs to physically sever a connection to quarantine a compromised server, they cannot afford to waste 20 minutes tracing an unlabeled yellow cable through a spaghetti monster of wiring.
That makes perfect sense. Poor physical maintenance delays the incident response.
Exactly. Seconds count during a breach.
All right, so the vulnerabilities are there, whether from bad protocol design, lazy passwords, or office politics. Now let's move to the attack playbook.
The fun part.
Right. Threat actors don't just stumble through these windows by accident. They have a highly systematic, almost militaristic process for finding and exploiting them.
They absolutely do.
Let's start with their weapon of choice, malware, malicious software. We hear terms like virus, worm, and Trojan used interchangeably all the time, but the notes make it clear that the mechanical differences between them are huge.
Yeah, the mechanism of transmission is everything. So a virus is a piece of malicious code that inserts a copy of itself into another legitimate program.
So it needs a host file.
Right. But more importantly, it requires human action to execute. A virus sits completely dormant until an unsuspecting user opens the infected email attachment or double-clicks the file.
Okay, so what about a worm?
A worm is fundamentally different. A worm is standalone software. It does not need a host program, and it definitely does not need human help.
Wait, really? It just moves on its own?
Yeah. Once a worm finds a vulnerability and breaches a network, it replicates and travels across the internal network entirely autonomously, just seeking out new machines to infect.
That is terrifying. And then you have the Trojan horse.
Right, the Trojan. Now, this doesn't self-replicate like a worm. A Trojan relies entirely on human gullibility.
So disguises itself.
Exactly. It poses as something helpful. A free utility program, a fake PDF invoice, maybe a software update. You think you're downloading something legitimate, but you are actively installing the malware yourself.
And Trojans are notorious for quietly creating those backdoors,
Oh,
right? Giving the attacker ongoing invisible access long after you close the fake file.
precisely. But, before a threat actor even launches a piece of malware, they have to map the battlefield.
Right, the reconnaissance phase.
Yeah, it's basically an unauthorized scouting mission to discover the systems and the specific vulnerabilities before the actual attack begins.
And the sources say this happens in 3 distinct stages, starting with internet queries.
Stage 1 is just using open source intelligence.
Like Googling.
Literally, yes.
Yeah.
Threat actors use organization websites, Google, and internet registry tools, like Whoisn't Lookup. This isn't even hacking yet.
It's just reading public info.
Exactly. It's reading the internet's public phone book.
Hmm.
Tools like Who's tell anyone who asks who registered a specific domain name, their contact info, and the general IP address space that organization controls.
So they're just drawing a rough map of the target's digital footprint.
Right. And once they have that IP address space, they move to stage 2, the ping sweep.
Okay, so they use automated tools to systematically ping every single address in that range, just to see which IP addresses send a response back. Isn't a ping sweep essentially like a digital burglar walking down a neighborhood street at 2 a.m., knocking on every single front door, just to see which houses have someone awake inside?
That is a great analogy. The premise is very similar, but scale up the magnitude, right? Imagine if that burglar could walk down every street in an entire city and knock on 10,000 doors simultaneously in a fraction of a second.
Wow, okay, that puts it in perspective.
That is the reality of an automated ping sweep. They are rapidly sweeping the entire grid to find the awake machines.
And once they have a list of active IP addresses, they move to stage 3, the port scan.
So they found the awake houses. Now they need to find the specific unlocked window.
Right. They probe those specific active IP addresses to discover which services or ports are open.
Exactly. And a port is basically just a numbered door on the machine used for a specific type of traffic.
Like port 22 versus port 23.
Good example. So port 22 is generally used for SSH, which is a highly encrypted armored door used for secure remote administration.
Hard to break into.
Very hard. But port 23 is used for an older protocol called Telnet. Telnet sends all its data, including passwords, in plain text.
Oh, yikes. So it's basically a flimsy screen door.
Exactly. If a port scan reveals that port 23 is open and listening, the threat actor knows exactly where to apply pressure.
Okay, so the reconnaissance is done. They found the vulnerability. Now the actual access attacks begin. They break in to view, alter, or steal information.
Right, and they have a few ways to do this.
There are brute force password attacks, obviously, where automated software just rapidly guesses millions of password combinations. But the techniques that really bend the rules of the network are trust exploitation and port redirection.
Yeah, these are much more sophisticated. Trust exploitation uses the network's own architecture against it.
How so?
Well, systems within a corporate network often have to trust each other to function smoothly, right? Let's say System A is the highly protected database holding all the valuable financial records.
Okay.
System A trusts System B, which is just a lower-level, poorly protected print server.
I see where this is going.
Right. The threat actor doesn't waste time trying to crack the heavy encryption on System A. They target the weak print server, System B. Once they compromise that server, they use its built-in trusted relationship to slide right past the defenses of System A.
It's literally like breaking into the security guard's car to steal his ID badge and then just waving that badge to walk through the heavily fortified front doors of the bank.
That's exactly what it is.
And port redirection operates on a similar pivot mechanism, right?
It does. In port redirection, the attacker uses a compromised machine as a relay station. They might connect to host A, which they've already broken into using that encrypted port 22 we mentioned.
Okay.
Once inside host A, they initiate a completely new connection out to host B, leveraging the internal trust host B has for host A.
So the attack looks like it's coming from a friendly machine inside the building.
Exactly, rather than a hostile actor on the outside.
This level of deception brings us to the man-in-the-middle attack. Put me in the scenario. How does a man-in-the-middle attack actually work in practice?
Sure. Picture yourself sitting at a local coffee shop. You connect your laptop to the free public Wi-Fi and type in the URL for your bank.
Pretty standard.
You believe your laptop is communicating directly with the bank's secure server. But a threat actor is sitting 2 tables away, running software that aggressively intercepts all the traffic on that Wi-Fi network.
Oh, wow.
So your laptop sends the request for the login page. The attacker intercepts it, silently forwards that request to the actual bank, receives the real login page from the bank, and then hands that page back to you.
So I'm looking at what appears to be my legitimate banking site.
You are. It looks completely normal.
Yeah.
But the attacker is an invisible intermediary passing notes between you and the bank.
Man.
When you type in your username and password, you hand it directly to the attacker, who copies it before passing it along to the bank to keep the illusion alive.
It completely shatters the integrity of the communication channel without you ever realizing there's a third party involved.
Precisely.
And finally, rounding out the attack playbook, we have denial of service, or DOS. As we covered earlier, this is about flooding a system with garbage traffic so authorized people can't use it.
Right.
But the notes highlight a massive difference in scale between a standard DOS and a DDoS, a distributed denial of service.
Yeah, it really comes down to the asymmetry of cyber warfare. A standard DOS originates from a single source. It's one computer trying to overwhelm one server.
Which is fairly easy to stop, right?
Usually, yes. It's relatively easy for a network defender to spot that single hostile IP address and block it. But a distributed denial of service is a coordinated assault.
Using a botnet.
Exactly. A threat actor uses a command and control server to hijack a botnet. This is a vast army of zombie devices. Thousands of compromised laptops, webcams, and even smart refrigerators across the globe.
Smart refrigerators, really?
Yes, IoT devices are notorious for this. At the press of a button, the attacker directs all 100,000 devices to simultaneously flood the target server.
And because the malicious traffic is pouring in from thousands of different, seemingly legitimate IP addresses worldwide,
it becomes exponentially harder to filter the bad traffic from the good.
so it takes an attacker one click to weaponize 100,000 smart fridges, but it takes a team of cybersecurity experts working around the clock to stop it.
That's the asymmetry of it, yeah.
With an attack playbook this sophisticated, I mean, a single password or a basic antivirus program just isn't going to save anyone. How do network administrators actually build a fortress to fight this?
They utilize a strategy called defense in depth.
Defense in depth.
It's a philosophy of layering. You never rely on a single safeguard. If an attacker breaches the outer wall, they should immediately hit a second wall and a third.
So layered security.
Right. The architecture typically starts at the very edge of the network with a VPN router, which provides a secure, encrypted tunnel for remote workers to access the network safely from the outside.
And behind that VPN router is the firewall. But not just any firewall. The notes specifically mention an ASA firewall utilizing stateful inspection. Let's unpack that jargon. What makes a firewall stateful?
Okay, think of a standard old-school firewall as a basic ticket taker. It looks at a data packet, checks the address, and lets it in if the address is allowed on the list.
Pretty simple.
Right, but a firewall with stateful inspection is much smarter. It acts more like an incredibly observant bouncer at a club. It actually remembers the context of the conversation.
No, I like that analogy.
So if an employee inside the corporate network requests a web page, the stateful firewall remembers that outbound request. When the web page data arrives a second later, the bouncer knows it was invited and lets it in.
But if a stranger from the outside tries to shove data through the door unprompted,
The bouncer checks the state table, realizes nobody inside asked for this traffic, and drops it immediately.
that makes perfect sense. But the layers don't stop at the bouncer. Behind the firewall, you have an IPS, an intrusion prevention system.
Right, the IPS.
So if the firewall is the bouncer at the front door, the IPS is the undercover security team actively patrolling the hallways, right?
That is a perfect way to put it. It monitors the traffic that was allowed inside, constantly scanning for malicious patterns in real time, and it actually has the authority to step in and kill a connection if someone starts acting suspiciously.
And working alongside the IPS are the ESA and WSA, the email security appliance and web security appliance.
Think of those as the mailroom inspectors. They tear open incoming emails and web traffic to aggressively filter out spam, phishing attempts, and malware payloads before they ever reach an employee's inbox.
Now, at the core of all these layers is the AAA framework, This is the primary system for access control across the network. AAA stands for authentication, authorization, and accounting.
Right.
The simplest way to understand this, according to the source, is to compare it to a credit card.
Yeah, it's a great metaphor.
So authentication is the ID check at the register, verifying you are who you say you are. Authorization is your credit limit, the system checking the rules to see exactly what you are permitted to do once you're inside.
Exactly.
And accounting is your monthly statement, the meticulous, unalterable log of exactly what you did, when you did it, and what files you accessed.
It really is a brilliant way to conceptualize it. Now, we established that the fundamental rule of firewall operation is default denial from the outside, right? Traffic originating from the internet trying to initiate a connection inward is blocked.
Right, the bouncer stops it.
But this creates a practical problem for businesses.
Oh.
What if you have a public-facing web server? You want external customers to access your website.
Yeah, you obviously can't hide your marketing website behind a firewall that drops all outside traffic. Nobody would see it.
Exactly why network architects build a DMZ, or demilitarized zone. Think of the DMZ as the ground floor public lobby of a highly secure corporate skyscraper. The public can walk in off the street, read the directory, and interact with the receptionist. But they cannot get past the security turnstiles to take the elevator up to the private offices.
So by placing public-facing servers in the DMZ, a separate, isolated network segment, a company allows the world to access specific services without ever exposing the internal, trusted network to the open internet.
Precisely. You get the best of both worlds.
So we have the defense in depth layers, the AAA framework tracking every move, and the DMZ acting as the public lobby. But maintaining all this requires strict operational hygiene.
It takes a lot of work.
You have to back up configurations and iOS images. And just to clarify for everyone listening, when we say iOS in this context, we aren't talking about the operating system on an iPhone.
Good distinction, yeah.
We're talking about Cisco's Internetwork operating system, the foundational software that runs their enterprise routers and switches.
Right. If an attacker corrupts that core routing software, the hardware just becomes a very expensive brick. Validating those backups offline is absolutely critical.
There's also a feature called AutoSecure mentioned in the notes.
AutoSecure is interesting. It's a command line tool on Cisco routers that attempts to automatically lock down the device. It disables vulnerable default services and enhances security settings, basically with a single command.
Sounds like a magic bullet.
Well, network engineers will warn you that it is definitely not a silver bullet. It establishes a baseline, which is great, but you still need strong fundamental practices. You still have to manually change default usernames, restrict physical access to the hardware, and enforce rigorous password policies.
The password policies we all know and hate.
The bane of our existence.
At least 8 characters, preferably 10 or more. A mix of uppercase, lowercase, numbers, and symbols. No dictionary words, no personal information.
Yeah.
The recommendation is literally to use deliberately misspelled words or entirely random alphanumeric strings. Don't use secret. Use a string of garbage characters.
Which is hard to remember.
Very. And that highlights perhaps the most profound point in this entire discussion about endpoint security. The hardest part of securing the laptops, phones, and desktops on a network isn't the technology, it's the people.
It always comes back to the human element. Always. The technology can process millions of packets a second. It can encrypt traffic flawlessly and analyze behavioral patterns in real time. But the system is entirely dependent on users who are inherently fallible.
And this is the part that really resonated with me. When addressing how to keep endpoint software updated and patched to fight off the latest malware strains, the consensus in the notes is that the best long-term solution is to configure systems to automatically download and install updates with absolutely zero user intervention required.
Zero.
I just love the dark irony of that. The ultimate mitigation strategy for a highly technical billion-dollar defense system is to literally take the controls out of human hands because we are simply too lazy, too distracted, or too unreliable to click the update button.
The irony is unavoidable. I mean, automatic updates remove human agency from patch management precisely because human agency is the vulnerability.
Wow.
If an organization's security posture relies on employees voluntarily stopping their workflow, rebooting their machines, and applying security patches, that network will remain perpetually vulnerable. the window will always be left slightly ajar.
So we have really mapped the battlefield today. We looked at the threat landscape, the information theft, the silent, lingering danger of data manipulation.
Yeah, that integrity piece.
We found the open doors through protocol flaws, bad configuration, and the hubris of office politics. We walked through the attacker's playbook, the rapid-fire reconnaissance of a ping sweep, trust exploitation, and the sheer scale of DDoS attacks.
That's a lot to take in.
It is. And we saw how network architects build digital fortresses using defense-in-depth, stateful bouncers at the door, and ultimately taking the human element out of the loop with automatic updates. It's just a constant, invisible war going on all around us.
It never stops.
Every time you click Remind Me tomorrow on a software update, every time you painstakingly type out a chaotic, deliberately misspelled password, or every time you log onto public Wi-Fi at a coffee shop,
Yeah.
you are actively participating in this digital arms race.
You're an active participant, whether you want to be or not. And, this raises an important question to leave you with, building exactly on that reality of human fallibility.
Right.
We've established that our own psychology, our implicit trust, our laziness with updates, our office politics, is inherently the biggest vulnerability in any network.
Yeah.
So, as cyber threats become exponentially more automated and sophisticated, will the future of cyber defense eventually require AI systems to proactively lock humans out of managing their own networks entirely, simply to keep them safe from themselves?
Taking the keys away from the humans just to protect the house. Because as we established right at the beginning, setting up a network without securing it is like opening every door and window to your home, then going on vacation. Don't leave your digital windows open.